the key, I think, to solving physics problems is to be able to describe verbally your thoughts long before you write anything down. So here we have a copper rod, which is slightly large, and a steel sleeve, which is a little bit smaller. Now, if you heat the sleeve, it will expand. You can move it down there, let it come back to equilibrium, and an equilibrium temperature, which happened to be at 25 degrees C, I believe. Is that right? 25 degrees C. Then it will shrink and hold tight. Great. But then the problem goes on to say you're going to go up into the Arctic winter. And that means the temperature is going to go well below this value. And it says at what temperature will they separate? Is that how it's worded?
Yes.
In other words, it cools down and both the copper rod and the steel sleeve will shrink. The implication is that the copper rod will shrink faster than the steel sleeve. Is there any way you could confirm that suspicion? The implication is copper shrinks more than steel. How would you know it's true? What do you think?
The alpha of the steel is smaller than the alpha of the copper.
That's exactly right. For copper, the alpha, the coefficient of linear expansion, 16.6 times 10 to the minus 6. And for steel, it's 11 times that. Because the alpha is bigger, the change in volume is going to be bigger. The change in diameter, the change in whatever, the change is going to be larger. So it's true, if you cool it down enough, the copper rod could get to be exactly the same diameter as the steel sleeve. That's when they'll separate, right? So the key issue on this problem, I think, is to say, find the temperature at which the diameter of the rod equals the diameter of the sleeve. That's what I would say. In fact, my strategy find delta T such that the diameter of the copper rod equals the diameter of the steel sleeve. But of course, the diameter is going to be the initial diameter minus delta D. Why? Because we're cooling it. That's where the negative sign comes from. Is that okay? So it's okay to put the negative sign in there, which now could be simply written as the initial diameter minus the initial diameter alpha delta T. Great, we're ready now. The strategy really is finished, although I think I would write this one last line on strategy, and that is D naught copper minus D naught copper alpha copper delta T should equal D naught steel minus D naught steel alpha steel delta T. I suppose that would be a good thing to put down as your final comment on strategy. This is more. And really, the only thing we seek is delta T. So I suspect then that I might write like this. Under tactics, I would write D naught copper minus D naught steel equals what? D naught copper alpha copper delta T minus D naught steel alpha steel delta T. I can imagine factoring the delta T out and dividing by what's left so that delta T is equal to D naught copper, D naught steel, D naught copper, alpha copper minus D naught steel, alpha steel. We now have a formula for delta T. Let's put the correct numbers in the correct places with the correct values. So D naught copper is 1.001 centimeters, 1.000 centimeters, just to make the point, and 1.001 centimeters times 16.6 times 10 to the minus 6 per Kelvin minus 1.000 centimeters, again just to make the point, 11 10 to the minus 6 per Kelvin, like that. Perhaps here I could easily demonstrate units consistency. There is a centimeters in common upstairs and downstairs, leaving 1 over kelvins, so the answer is going to be in kelvins. So now that I've written all the correct numbers in the correct places with the correct units, now I can start simplifying things a little bit. For example, delta T would be 0.001 times 10 to the 6 kelvins divided by 1.001 times 16.6 minus, and I guess I'll make the point, 1.000 times 11. Would you check my calculation? I think I got 178. I got 178 kelvins. Let me check mine. Well, would you redo the math? Because I'm going to use that number as my key. Let me make sure that's what I got. Yeah, I got 178. Of course, you've got to go back and remember it's going to drop 178 degrees. 178 kelvins is the same as 178 degrees Celsius. So T final is going to be T naught minus delta T, which is of course 25 degrees C, minus 178 degrees C. That's 153 degrees C with a negative sign. There's the final number. Minus 153 degrees C. As engineers, you conclude no problem. The Arctic winter never gets that cold. It won't fall apart. I would consider this the main part of the problem right here. This is the part here that's the main part of the problem. Once you get to this stage, you guys do math pretty good. I'm sure you would get here. I'm pretty sure, you know what? Putting the correct numbers in the correct places with the correct units seems to be harder than doing the math. The arithmetic seems to be harder than the math. For me and you meaning not you personally, but students as well as me, I have the same problem. I seem to have more trouble with the arithmetic. So I have to start getting real cautious at this stage. Very careful about the correct numbers in the correct places with the correct units. All right, that's quiz number 2. Are there any questions, comments, cares, or concerns? I have everything graded from last week and recorded. When we meet for lab this afternoon, is it 1 o'clock? 1:20? What time do we do this afternoon? Say again? 2:30. 2:30? Okay. Good, we're all lunch. Okay, 2:30. When we meet at 2:30, I will have your homeworks from last week ready. And speaking of lab, that's what we're going to spend a little time on today. Typically, what I would like to do is spend a few moments during the lecture part of the class preparing for the lab. Today is our very first lab of the system, so I'd like to talk a little bit with you about laboratory, my philosophy, my grading, and so on. You may want to take notes because this is important. First off, laboratories are scheduled for 3 hours, but you only get 1 unit. Why? I think you're aware of the old rule of 2 for 1. You're supposed to study 2 hours outside for every 1 hour in class. Like for example, the lecture part of this class is a 4-unit class. You should be studying an additional 8 hours minimum. So it's assumed that you will put in 12 hours of study for a 4-unit class. That's the basic philosophy in school. The reason you get 1 unit for a 3-hour lab is because you're supposed to get it completely finished in laboratory. You're supposed to finish before you leave. You don't do an additional outside study. You get the lab done in 3 hours and you get 1 unit for it. So that's the idea. People often ask about that. Why is there only 1 unit of credit for a 3-hour class? It's because of the old rule of 2 for 1. What you'll be turning in is a lab write-up, and let me express to you, I have 5 things that I look for specifically in a lab write-up, and I would like you to create a heading for each one of these 5 each time you do a lab write-up. Let me just list them and then I'll describe them, okay? So there are 5 what I might call paragraph headings in a lab. Number 1 is purpose. Number 2 is procedures. 3 is data. 4 is summary. The last one, number 5, is conclusions. So you should have 5 headings: purpose, procedure, data, summary, and conclusions. Now let me describe each one, because some of them I look at and some of them I hardly look at. For example, purpose, extremely important. And by the way, unlike previous lab classes, where almost always the teacher comes in and quite explicitly tells you the purpose of the experiment, that makes it easy. Unfortunately, I'm not going to make it so easy. I'm going to generally describe the lab, what we're doing, what we're measuring, that kind of thing. But I really want you to come up with a purpose statement. So, typically, like on a Monday morning, we'll talk a little bit about how the lab is done. Between Monday morning and Monday afternoon, I would like you to come up with your own purpose statement. I do make a warning to you. Don't ever, in a purpose statement for a lab for this class, don't ever say, we intend to prove something. Because, boy, that's almost impossible to do. It's almost impossible to prove something. To absolutely prove something, what do you have to do? You have to do an infinite number of experiments. You don't have time. So, to use a word like prove, it's a big word, it's a big goal, it's a big major undertaking. You're not going to accomplish it in 3 hours. So you, in a way, set yourself up for failure with the first purpose statement. You say, I intend to prove something, you're going to fail. So don't do that. I'm going to measure this. I'm going to test this equation. Those kinds of statements are what you put in purpose. The purpose of this experiment is to test this theory, or the purpose of this is to measure this value. I expect it to be succinct, just a few lines. Remember, this is not an English class. In English class, I expect you to do a 20-page paper. We want to have very, very succinct and brief statements. Procedure section, rarely do I look at that. This is notes to yourself, especially about equipment you've never used before. Now let me explain to you, this is important. There's a real good chance we're going to have a laboratory final exam where you, individually, will be given equipment to redo one of our laboratories. And you have to be able to completely redo the laboratory with nothing more than your own notes. So, if you come across a piece of equipment you've never seen before, you might be drawing pictures or taking pictures, writing down details about how you use this piece of equipment, whereas if you're asked to measure a temperature with a thermometer, you probably don't have to go into too much detail because the next time you're given a thermometer, you'll know how to use it. So the procedures section is a section I consider your personal notes. You're always thinking to yourself, if I had to do this experiment all by myself with nothing but my notes, what do I need to write down so that I can remember how to use this equipment? Or what are the steps in doing this particular experiment? I think the most important thing to do during procedures is to keep in mind that I may set equipment in front of you and say, redo this experiment, and you're going to have to remember which experiment, what are the procedures, well, how do you read the equipment, all that stuff. So make notes here.